Today we are going to discuss a very important motion called simple harmonic motion. As you know, there are different types of motions like linear motion, circular motion and oscillatory motion. Simple harmonic motion is a special type of oscillatory motion where acceleration is directly proportional to displacement and directed opposite displacement. And the circular motion and simple harmonic motion, they are very strongly correlated. Let us see what is that correlation. Imagine a person moving in a circular path of radius r. Let us say P is that person. Okay. It's like if tip of this pen moves in a circular path, if you place a projector the other side, and its image will be in oscillatory motion. So the projection of uniform circular motion is called simple harmonic motion. Let us say the projection of P is Q. Q is the projection of P. So this side you can say imagine projection. This length usually we call as projection. At t is equal to 0, the particle P starts rotating along the circular path of radius r. At t is equal to 0, its projection is at Q. After small interval of time, the P has moved to P dash position. Its projection on y-axis moved to Q to Q dash. Q to Q dash. So the angle turned by this radius vector is called angular displacement. Theta is the angular displacement of P, which is in uniform circular motion. In the same time, the linear displacement of Q is y, which is moving along y-axis. Let us find out the relation between these two, that is theta and y. Theta is with respect to P, y is with respect to Q. We know that sin theta is equal to opposite side y by radius r. So y is equal to r sin theta. So let us change the nomenclature. Here r is called radius of the circular path. Okay. Its projection is moving along y-axis. The maximum displacement of the Q from the mean position is r. The same r we call as amplitude. The maximum displacement from the mean position is called amplitude. So the same radius for P, it becomes amplitude for Q. The second thing is, and angular velocity omega is equal to theta by t. The theta is equal to omega t. So this is the equation for the displacement of Q, which is moving along x-axis, y-axis. Let us find out if v is the velocity of P, which is nothing but r omega. Now I am changing r omega to a omega. Okay. Its projection. Sometimes this projection also can be called as the image. Okay. Q is the image of P. Its component along y-axis is a omega cos theta. Theta is nothing but omega t. That means if P moves with a uniform speed along the circular path, its image along y-axis moves with the speed a omega cos omega t. So the velocity of P is Q is a omega cos omega t. or even if you differentiate this displacement with respect to time, you will get the same formula. Displacement and velocity of q, which is moving along y-axis. Let us find out the acceleration of both the p and q. So let us say the particle is moving in xy plane. The particle P, its projection moves along y-axis. We know that the acceleration of the particle which is in circular path is towards center. It is equal to r omega square, a omega square. The acceleration is towards center at a given instant. If you resolve this acceleration into two components, this angle is same as this angle. It is a omega square cos omega, sin omega t. The component of acceleration a omega square along y-axis is a omega square sin omega t. That is the acceleration of q is a omega square sin omega t, and when it is moving up, the acceleration is down minus. The acceleration a is equal to minus a omega square sin omega t. But we know that a sin omega t is y, a is equal to omega square y, which is a very, very important condition for SHM. Any particle said to be in SHM, if its acceleration is directly proportional to its displacement, directed opposite to displacement. A is equal to minus omega square. For any system, we have many like simple pendulum, spring mass system, or an object oscillating in a fluid. For every SHM, you have to prove that A is equal to minus omega square y. From that, we can find the angular frequency y. From angular frequency, we can find its time period, which is equal to 2 pi by t. Okay. So this is a very, very sufficient and necessary condition for SHM. Okay. So that's what the basic idea of SHM. Okay. When a particle is in a uniform circular motion, its projection is in SHM, and the corresponding equations are A is equal to y is equal to a sin omega t, v is equal to a omega cos omega t, and acceleration a is equal to minus a omega square sin omega t, which is nothing but a is equal to minus omega square. And one more important thing in SHM is phase. Let us try to understand what is the term of phase. Phase, which plays a very, very important role in SHM. Let us say, if you take a reference circle, sometimes we call this as a reference circle. In xy plane, so P is the initial position, that is at t is equal to 0, its projection is q. Okay. Q is called mean position. After some time, P has moved to P prime after time t. If projection Q move to Q dash. Okay, fine. This angle theta we call as angular displacement of P. In the same time, the linear displacement of Q is y. Okay, fine. and already we derived y is equal to a sin theta or y is equal to a sin omega t. Fine. Now, if you are in circular motion, theta is called angular displacement, but with respect to q, which is oscillating along y-axis, this same theta is called phase. The very, very important, or phase angle. Phase or phase angle. Okay. That means this omega t is called phase. Okay. Phase is the state of a vibrating particle. A state of the vibrating particle. If I know the phase, I can find where the particle when it is oscillating. Let us say theta is equal to 0. That is, P is at this position, its projection is at Q. Okay. That means phase is equal to 0 means the particle is at Q, center of the circle. As it moves along y-axis, when the P is here, Q is also here, phase of this point is 90. 0, 90, 180, 270, 360. Angles, this theta value. Okay. When theta is 0, the particle is at mean position. When theta is 90, the particle is at right extreme position. When theta is 180, the particle is at center and try to move down. Okay. There is a difference between 0 and 180. And theta is 270, the particle is here. Theta is 360, particle is just come back to again the original position. So these angles are called phase angles, which decides the y value in turn. Okay. Fine. Sometimes you have to use phase difference, usually denoted by pi. What is phase difference? In this reference circle, we are assuming that the particle is P is starting at this position, so that its projection is starting from mean position. But it is not the case always. Sometimes this particle P may start from somewhere else where theta is equal to, for example, let us say pi value is 30 degrees. That means its projection y is equal to a by 2. So it may start from this position. Okay. So the starting value of phase is called phase difference. The starting value of phase is called phase difference. The phase difference is also called initial phase or epoch. Okay. This phase difference will give us an idea where the particle start oscillating. Okay. That's why in general we write y is equal to a sin omega t plus or minus pi. This is the complete equation of SHM. Y is equal to a sin omega t plus or minus pi. Depending on the starting from here or here, take plus or minus pi. Okay. This is the complete equation for here. Y is called displacement, a is called amplitude, omega is the angular frequency, which is nothing but 2 pi by t, t is the time which is a variable, and pi is called initial phase. Okay. This is the basic theory of a simple harmonic motion by taking a reference circle. Let us go to a direct the real systems where they execute simple harmonic motion.